The nucleus. This tiny, dense core is the arena, the battlefield, where these titanic forces of fission and fusion are unleashed. Fission. This is the art of splitting the atom. In simple terms, nuclear fission is what happens when a heavy, kind of unstable nucleus, think uranium, splits apart into two or more smaller, lighter nuclei. And these little fragments that are left over, they're called daughter nuclei. Now, this splitting can actually happen in a couple of ways. On one hand, you've got spontaneous fission. This is just a rare form of natural radioactivity. It just happens on its own. But the one we've figured out how to harness is induced fission. This is where we intentionally trigger the split by hitting the nucleus with a particle, almost always a neutron. This is the method that powers our nuclear reactors and, well, nuclear weapons too. A really great way to picture this is with something called the liquid drop model. Imagine the nucleus is like a wobbly drop of liquid. When a neutron comes in and hits it, that drop starts to jiggle and deform. It stretches out, gets thin in the middle, and then snap. It splits into two smaller droplets. And in the process releases a huge burst of energy, and this part is absolutely crucial, it also releases 2 or 3 extra neutrons. And if we dive into the details, there's some fascinating stuff here. For instance, the splitting is almost always binary, meaning you get 2 daughter nuclei that are roughly comparable in size. But in a very rare event, we're talking about 4 times in every 1,000 fissions, you can get a ternary fission with 3 daughter nuclei. And the energy release, it's just staggering. Splitting just one of these atoms unleashes millions of times more energy than burning a single molecule of coal. Now remember, those extra neutrons we just mentioned, they are the secret sauce. They're the key to unlocking fission's immense power. They create a cascade, a domino effect, which brings us to the great challenge of controlling the chain reaction. And here it is. It really is like a set of cosmic dominoes. The neutrons released from one fission event fly off and hit other nuclei, triggering more fissions. Those fissions release more neutrons, which trigger even more fissions. You get this self-sustaining, cascading release of energy that just keeps going. In a controlled chain reaction, we carefully manage things so that only one neutron from each split goes on to cause exactly one more. This gives us a steady, sustained release of energy, perfect for a nuclear power plant. Now, if you just let all those extra neutrons run wild and trigger as many new fissions as they can, you get an uncontrolled, exponential release of energy. And that is an atomic bomb. So how on earth do we control it? It all comes down to a number, a sort of magic number called the neutron reproduction factor, or K. If K is less than 1, the reaction is subcritical, and it just fizzles out. If K is greater than 1, it's supercritical, and it accelerates exponentially. The sweet spot, the goal for a power plant, is to get K to equal exactly 1. That's what we call a critical state, a perfectly stable, self-sustaining reaction. But as you can imagine, hitting that perfect balance isn't easy. There are some real-world difficulties. For starters, there's fuel purity. Natural uranium is almost entirely uranium-238, which tends to just absorb neutrons without splitting, effectively stopping the reaction. The good stuff, the fissionable U-235, makes up less than 1% of natural ore. The other problem is neutron speed. Fission spits out really fast neutrons, but it turns out U-235 is much better at capturing slow ones. So we have to use special materials called moderators to slow those neutrons down to just the right speed. Okay, so we've spent a lot of time talking about splitting things apart. Let's flip the coin and look at the other side. If fission is about destruction, fusion is all about creation. It's about building things up. This is the power of the stars. So, nuclear fusion is the process where 2 light atomic nuclei, say isotopes of hydrogen, combine or fuse together to form a single, heavier nucleus. And just like fission, this process releases an absolutely immense amount of energy. But there's a huge catch here. Both of those nuclei are positively charged, which means they desperately want to repel each other. It's like trying to force the same ends of 2 powerful magnets together. To get them to fuse, you have to smash them together with incredible force, enough to overcome that natural repulsion and let the strong nuclear force take over and bind them. And how much force are we talking about? Well, you essentially have to recreate the conditions found in the core of a star. We are talking about a minimum temperature of 10 million degrees Celsius. That's why building a fusion reactor here on Earth is one of the greatest scientific and engineering challenges we've ever faced. We're literally trying to build a star in a bottle. And all of this leads us to the biggest, most fundamental question of all. We've just seen that splitting heavy atoms releases energy, and that joining light atoms also releases energy. How is that possible? What is the secret behind all of nuclear energy? No, seriously, stop and think about that for a second. How can you get energy from both breaking something massive apart and from building something new? It seems like a complete paradox, right? The answer, beautifully, is revealed in this one graph, the binding energy curve. The best way to think of this is as a chart of nuclear stability. The higher up an element is on this curve, the more stable its nucleus is. And right there at the very peak, you see iron 56. It's the most stable element in the universe. Now look what happens. Fission takes a really heavy element from the far right and splits it into lighter pieces that are higher up the curve. They're more stable. Fusion takes very light elements from the far left and joins them into a heavier one that's also higher up the curve. Both processes are climbing the hill toward stability, and that difference in energy, that climb, is what gets released. But where does that energy actually come from? It comes from mass itself, all explained by the single most famous equation in the history of science, E equals mc squared. In both fission and fusion, if you were to weigh the final products, they would actually weigh a tiny, tiny bit less than the initial parts. That tiny amount of missing mass isn't really missing. It's been converted directly into a tremendous amount of energy.